Let's continue section 3.1, integration by part, more examples. So here I have integrating x squared sine of x dx. So for this one, we have x squared, which is a polynomial function, sine of x, which is a trig function. So according to the rule, we are going to let u equals to sine of x. Actually, we should using the u to be the x squared, and then dv equal to sine of x dx. The reason for that is when we're taking the derivatives of the u, x squared, which is easier to do, and just in case we need to do the integration by part multiple times, eventually it will go to 1 or 0. Then the integration of the v is not hard. Negative cosine of x dx, negative cosine of x, the derivative of cosine of x is negative sine of x. So I need to have a negative to make it a positive. Then uv negative x squared cosine of x minus the integration of 2x or negative 2x cosine of x dx. So to make it looks a little nicer, let's move the negative 2 out. I got integral x cosine of x dx. Then let's do the integrations for the second part. Let u equal to x, then du is equal to dx. Dv equal to cosine of x dx. V is equals to sine of x dx. No more dx, sine of x. Then, according to the integration by part, let's copy down the front stuff. It's going to be uv x sine of x minus the integration of the sine of x dx, which we know is easy to find the integration. Which is negative cosine of x. So make it a little bit nicer, negative x squared cosine of x plus 2. If you want to multiply 2x sine of x plus 2 cosine of x plus c. Keep in mind, on the rule sometimes, the rule we have, the LIATE, sometimes may not work. So it really depends on the problem. And then you can decide, I mean, most of the cases this will works, the LIATI. You're going to choose your u if there's a logarithmic first, or inverse trig, or algebra like polynomials, or trig, or exponential. However, there are cases that it will fall. Just keep in mind. It's not really a lot of cases, just some cases. Now let's looking at another example. This time, I want it to be a definite integral. I want to integrate from 0 to 1 of tangent inverse x dx. Tangent inverse of x dx. So here I cheated a little bit. I know the formula for tangent inverse, or the integration of the tangent inverse. Oh, sorry, the derivative of the tangent inverse. So I'm going to let u equal to tangent inverse of x. Then du is equals to dx over 1 plus x squared. I'm going to let dv equal to dx. So v is equal to x. Using the integration by part, this is going to be uv x tangent inverse of x evaluated at 0, 1 minus the integration 0 to 1 of the v du x over 1 plus x squared dx. Now let's just figure out, to just make it simpler, let's figure out what is x tangent inverse of x, evaluate from 0 to 1. That is going to be 1 times tangent inverse of 1 minus 0 times tangent inverse of 0. Tangent inverse of 1, which is pi over 4. So this piece just simply ending up with pi over 4. Now how about the definite integral of 0 to 1 x over 1 plus x squared? We're going to use it, we're going to evaluate it using substitution method. So we're going to let u, this u is different than the previous u, is equals to 1 plus x squared. Then du is equals to 2x dx. So x dx is equal to 1/2 du. Okay, so x dx, x dx. So the integration now becomes to, let me change a color. Becomes to 1 over u du, 1/2 to the front. When x equals to 0, u is equals to 1 plus 0 squared, which is 1. When x equal to 1, u equal to 1 plus 1 squared, which is 2. So this one is going to be range from 1 to 2. Now we know that integral of 1 over u, this is going to be ln of u. Evaluate from 1 to 2. Then it's going to be ln of 2 minus ln of 1, where ln of 1 is going to be 0. So we ended up with pi over 4 minus 1/2 ln of 2, or ln of 2 over 2. So this is going to be 0. And that is our final answer for this definite integral evaluation. Now let's try one more example. Definite integral, evaluate from 0 to pi over 2 of x cosine of x dx. So first, let's use integration by part. Let u equal to x, du is equal to dx. dv is equal to cosine of x dx. Then v is equal to sine of x. Then the integration by part says this is going to be uv x sine of x, evaluate from 0 to pi over 2, minus the integration of 0 to pi over 2 sine of x dx. This is not too bad to evaluate it, or to find the integrations. So first thing first, the evaluation portions, we have pi over 2 sine of pi over 2 minus 0 times sine of 0. 0. Of course, this is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times sine of 0 is going to be 0. 0 times And then we're going to minus the integration of sine of x, which is going to be negative cosine of x, evaluate from 0 to pi over 2. So we ended up with sine of pi over 2 is 1, so pi over 2 plus cosine of pi over 2 minus cosine of 0. Minus and minus become 2 plus. Cosine of pi over 2 is going to be 0. Cosine of 0 is going to be 1. I should not circle that. So we ended up with pi over 2 plus 0 minus 1. And you can get decimal numbers. The decimal number is going to be pi over 2 minus 1, which is roughly about 0.571. But either answer will be fine, pi over 2 minus 1 or 0.571. And that's it for section 3.1, integration by part. So there are 3 videos for this section. The first video just briefly introduced what is integration by part, what is the formula, and some of the tricks, how to choose your U. Then we have 2 videos about the examples, how to solve, how to use integration by part to solve any of the integration problems. Be aware that there are simple integration problems, just like you just do the integrations. Or you can have, or there are problems you need to do integration by part twice. Or there are problems that you need to do integration by part once or maybe twice. At the end, you're going to using some algebras to solving for the actual integral instead of integrating it. And then lastly, we show the definite integral portions. And there are also another type of problems that combining, like this one, combining the integration by part with the U substitution. So here we're using the integration by part, here we're using the substitution method. So because those are skills, we can build up, we can make problem, we can using those skills to break down a very complex problem to something is manageable, is able to solve. Okay, I will see you in the next video.